Hey everyone, welcome to this section on the Parkinson's Disease Detection. According to the Parkinson's Foundation, the Parkinson's disease is a neurodegenerative disorder that affects predominantly dopamine-producing neurons in a specific area of the brain called the substantia nigra. And statistics show that close to 1 million people in the US are affected or have been diagnosed with the Parkinson's disease by the year 2020. In this tutorial session, we shall walk you through the data preparation. We shall first start by understanding the data, preparing this data. Then we shall move on to modeling. That is, we are going to build a model which we are going to train on this data in order to correctly diagnose the Parkinson's disease on the person. From there, we'll move on to training optimization, some visualizations, and then evaluation of the model, and finally testing and some corrective measures. So let's get started. Our first step will be to understand the problem at hand. So we could get to this link at mayoclinic.org. We would have to understand that the Parkinson's disease is a progressive nervous system disorder that affects movement. The symptoms start gradually, sometimes starting with a barely noticeable tremor in just one hand, as tremors are common, but the disorder also commonly causes stiffness or slowing of movement. For the symptoms of Parkinson's disease, we have a tremor, slowed movement, rigid muscles, impaired posture and balance, loss of automatic movements, speech changes, and writing changes. Consider this figure right here, drawn from this paper by Manuel Gil Martin, Juan Manuel Montero, and Ruben San Segundo, entitled Parkinson's Disease Detection from Drawing Movements Using Convolutional Neural Networks. Since we had seen previously that a patient suffering from Parkinson's disease would have a tremor or shaking, usually beginning in the limb, often in the hands and fingers, and also writing changes, that's difficulty in writing. A means of diagnosing the Parkinson's disease was derived from these symptoms. And the way this works is a patient is given a graphic tablet. In the case of this paper, on this data set, it was recorded on the Wacom CITIC 12WX graphics tablet. And when given this tablet and the pen, you are asked to put out some spiral drawings. And obviously, since a patient suffering from Parkinson's disease would have difficulty in writing, the measurements for such patients should be different from that of another person who isn't suffering from the Parkinson's disease. So this is a technique used in diagnosing the Parkinson's disease. The exact data gathered from this tablet is the X, Y, Z coordinates, pressure, and grip angle, as we could see right here. So the person is given a pen, and as you come up with the spiral drawings, information about the X, Y, and Z coordinates with respect to a given origin is noted, and then also information about the pressure you're applying on the tablet, and this grip angle is also noted. And it's based on this data that a public data set, or this public data set entitled the Parkinson's Disease Spiral Drawings using digitized graphic tablet data set was created. This data set includes spiral drawings from 77 people, 62 suffering from the Parkinson's disease, and 15 were healthy people. So now we've understood the task at hand, which entails taking data of the X, Y, Z, pressure, and grip angle when a person is drawing out spiral shapes on the tablet or on a graphics tablet. Now that we've understood the task, we can now move on to the data set. The data set is found on this link right here. This data set by Isenkole et al. and Erdogu et al. Is made available on the UCI machine learning repository site. And right here we have the dataset information. To obtain this dataset, suffice to click on this data folder right here. So you click on this and then you download the data. In this dataset, you would actually have these 3 folders. We just added this one. So here we have the dataset itself, controlled as a healthy patients. As you could see, we have 15 items, and then for the Parkinson's we have 25 items. But then there is another folder, this new dataset, which contains more. So that's why we have 62 items or 62 data points of people with the Parkinson disease. That's it. We have that. And then we also have those drawings, the spiral drawings right here. Nonetheless, we are going to make use of the information in this folder and this folder. In this Parkinson's folder, we have the train data made of 63 items, and then the validation data made of 14 items. Now you should note that this data set is imbalanced as we have more data points with people having the Parkinson's disease as compared to the controls or the people, the healthy people. The healthy people can be seen here with the C, starts with the C. Here we have control, and then here we have those with the Parkinson's disease, and the same for the validation set right here. Let's now click on one of these files. See this here. We see that we have this X. So here's our X, here's our Y, here's our Z. So here we have the X, Y, Z values at a given time, because the person or the patient is actually drawing up a spiral. So let's suppose that we are holding a pen, and then we'll fix an origin. So let's do something like this. Let's suppose that we have here X, Y. So here we have X, and then Z is coming out of the board, so we'll have something like this. So here we have Z. Now we'll put in these drawings and say we had this position 200 for the X. So here we had position 200, and here position say 204. Now we have this position initially, and then we start drawing. From here we could do this. So we have this kind of spiral which the person has been asked to draw. And so as a person just starts drawing, suppose we are at this position, as you start drawing, as we are moving, these different positions are being recorded. So at this point we record the X and the Y, that's the Y, and then the X, and then we put it out here. We record the Z component. We'll see how the Z component is 0, because if we are on a plane, then the Z component should be 0. So here we just recording these values continuously, and then we also recording from here the pressure, grip angle, timestamp, and test ID. And that's why we have this 4 other values right here. Now that we understand perfectly well the data which is found in these text files, we could also look at the length. So we see that we have 500, or rather 5,801 data points for this. Let's take this back up. Let's take some steps back. And then if we open up another, let's get back into the Parkinson's. We have training data. If we open up another file like this one, you see similar type of data. But here we have, instead from this, 5,506 data points. So we notice that for each data point we have different number of lines, which is normal since we don't take the same time in drawing out the spirals. Let's go ahead with the data preparation. We'll define those 2 files, PD and healthy. For the PD is a text file from a patient who has the Parkinson disease, and this is a text file for a healthy patient. Now we are going to understand why we need all these inputs subsequently. We shall create a function which will permit us go through all this data that's for each text file, we go through all these different data points right here. That's up to this 5,506 point, and then store all this in an array such that we could easily process it with Python. And here's the function in question. We call it genPoints. It generates the array. In this function, we take in the file name and then we output an array containing the file data. We start by defining this empty list right here. So we have this empty list, and then we open up the file, which you just call your directory. So let's call this file. So we have that file. We open up that file, and then for every line in the file, so we shall go line by line. For this line, for example, we are going to pack up these values in this empty list we defined right here. So that's why we have data list that append these values right here. Now note that this first line is actually a string. So let's copy this here so you could better understand exactly what's going on right in here. So here we have a string, or let's a line is that string. It has its values, and then we want to take each and every value. Notice how each of these values is separated by this semicolon. And so for every value we have in here, we want to do the split based on this semicolon. Now, the reason why we go up to this second to the last position is actually because in this line right here, the last position is occupied by the next line string. And so normally what we should be having here is this. So this is what we have, and we're not interested in getting this next line string, so that's why we take this off, and that's why we go up to this second to the last position. Now that we've had that and we've splitted our values, we pass this integer of x to convert this into integers. Let's do a simple demo. We could have for x in, or for L in line, we have that -1 dot split based on the semicolon. We are going to print out x, or rather L. So for each of those values, that's after splitting up this, we're going to print out L. So you see that this does exactly what we want. And now we could convert this into integer by taking that. You see we have this error, but let's get back to this, because the way we had defined this is actually n. The way we had defined this was such that we're considering that this last value we have here is the next line string, or the next line character. So we are going to just include that in this test and then run it again, and you see that everything works fine. So we extract all these values and then we pack it up in a list. So yeah, notice how we create this list. We pack this up in the list, and then we append it to the data list. And so now we have this data list which contains a given line, and with this for loop we repeat this for all the different lines. So for all the different lines, we're going to pack this up and then form this data list right here. Now next step is we simply convert this data list into a NumPy array, and then we specify that it's of type float. So this is going to be floats now, no more integers. And then for the next step, we're going to do some normalization. But before getting to this, let's first of all print out the values we obtain here. So let's run this, and there we go. We have this. Let's do shape. Oh, it's not that. So we have this as output, that shape actually. So we have the 5,506 by 7. Recall that we had 5,506 lines right here, which we could read here. And then the 7 is simply the different positions we have: 1, 2, 3, 4, 5, 6, and 7. Once we have this data, our next step will be to normalize it. Coming back to the text file, let's get back up. What we want to do exactly is one that for each and every column. That's for the x values, for all those x values, this x values right here, for all the y values, for all the z values, and so on and so forth. This data should be normalized. And so the normalization is not done across the rows. We're not normalizing across a row like this. We're instead normalizing across each and every column. So we normalize the x values, y up to the last. That said, that's why here we see that we do this. That's we pick all the rows. Let's uncomment this. We pick out all those rows, as you can see right here, and then we normalize through each and every column. So the normalization is done on each and every column. Since we have 7 of this, we go through I in range 7. So we do that normalization through those 7 different columns. Nonetheless, since these last 2 columns represent the timestamp and the test ID, it doesn't make sense to normalize the timestamp and this test ID. So we are going to do this for I in range 5. So we'll do that for the first 5 columns. We run this again. Let's take this off, and you see that we now have this normalized values right here. If you don't understand what normalization is about, you could just take it to be that supposing we have a set of values, or supposing we have a value x, to normalize this value we have that minus a mean divided by a standard deviation. So this is what we're doing. And so for say this x column, we want to normalize this particular value. We're going to find the mean value or the average value throughout this x column, and we're also going to find the standard deviation for this x column. And then we're going to take this value minus that mean divided by the standard deviation to obtain this new or this normalized value of this particular x value we have right here. And so that's why, as you could see here, we have the mean. With numpy we could get np.mean easily and np.std for standard deviation. Now that said, let's go ahead and see or visualize the data we're working with. So right here we have the 5 different columns. So here we'll modify this slightly since we now have 5 different columns. And then for each of these columns, we're going to print out the variations in data for both the txt file, or for both the Parkinson's disease patient and the healthy person. So now let's run this. We're having this error because we didn't run this first one right here. So let's run this again. And there we go. Here's our data. For more clarity, let's do this right here. We have this naming, and then here we have naming I and naming I. Run that again. We have the PDX, healthy X, PDY, healthy Y, PDZ, healthy Z, so on and so forth. And as you may have noticed, for the X values, that of the healthy patient appears smoother compared to that of the person with the Parkinson's disease. And then for the Z values, with the PD we actually have no value right here because the PDs are all zeros. And so when we normalize that, we get this empty plot right here. While for the healthy patient, we have this different type of Z plot. For the pressure, we could see a clear difference. We see how smooth this pressure curve for the healthy patient is as compared to that of the P patient right here. While for the grip angle, we have similar type of plots. And as you may have noticed, for the X values, that of the healthy patient appears smoother compared to that of the person with the Parkinson's disease. And then for the Z values, with the PD we actually have no value right here because the PDs are all zeros. And so when we normalize that, we get this empty plot right here. While for the healthy patient, we have this different type of Z plot. For the pressure, we could see a clear difference. We see how smooth this pressure curve for the healthy patient is as compared to that of the P patient right here. While for the grip angle, we have similar type of plots. In our deep learning with TensorFlow 2 course, we go deep into another point to notice. There is much information in these plots that we can't really perceive by just looking at them this way. Another way to represent this type of data which changes in time is to convert it into a spectrogram. That is, to convert these signals which are changing over time in the frequency domain. In our TensorFlow 2 course, we actually go in depth to explain how we could leave from the time domain into a frequency domain with a Fourier transform. We explain this in depth, and then finally with a short time Fourier transform. But yeah, we're just going straight forward to showing how we could leave from this time domain to a frequency domain using TensorFlow's signals model. In order to extract these spectrograms from our signals right here, we're going to define this getSpec method. It gets an input signal, which is practically the matrix which is outputted from this gen points right here. We get that, and then we're gonna go for I in the range 5, just as what we had right here. That's similar to this. And then in that, what we do is we obtain those spectrograms, that is the signals in the frequency domain, by applying this tf.signal.stft function. STFT stands for short time Fourier transform. And what we're passing in again is the column values of the inputs. Recall that each column represents each and every value we have here. So the X has its column, Y is column, Z is column, and so on and so forth. So each and every feature is represented with a given column. And so we are passing each and every column. And then we have this frame length and frame step parameters which are passed in. In our deep learning with TensorFlow 2 course, we explain in detail how and why we choose a given value for the frame length and the frame step. But yeah, we just take this value 512. Let's take half of this, so let's take 256. Since the output of this method right here is gonna be complex numbers, we actually convert this into real numbers with this absolute value function right here. And then we take the logarithms. Now we add this small value here because we have many values with zeros, and then we want to avoid having infinite values. Once this is done, for each and every column, we add this up or append this to the specs empty list which we've defined, because we're doing this for each column, so we're just packing it up in this empty list right here. Once we're done, we convert this into an array and we return the value. The next step will be to visualize just as what we did right here. So we have this. Here again we have the spectrogram. What it does is we have the getSpec, which takes in values from the gen points. Recall that this gen points we had here was responsible for generating this data. So once we generate this data by passing in PD, so we generate the data, we now pass it into the getSpec, which generates a spectrogram, and then we repeat the same for the healthy data. So we have the PD and the healthy data, which is passed and put in the spectrogram list right here. Then we do the plots. So we have the plots, and then we could run it. And there we go. Here's what these plots look like. You notice that there's some difference in the different spectrograms. this line right here is just above 10 while this line is below 10. For the y's, you see that they're kind of similar, and that's even clear from here. You see that these two are kind of similar as compared to the x plots right here, which are slightly different. And then we move to the next, that's the z's. For the z's, we have the PD, we have the spectrogram for the healthy, we have that. And then the pressure spectrogram gives us this for the PD and this for the healthy. While finally we have the grip angle spectrogram, which is this. And for the healthy, we also have the spectrogram right here. Now, it's important to note that these spectrograms are actually rotated spectrograms. As in this axis, we have the time, and in this axis, we have the frequency. Our problem has now been rephrased as what we're trying to do is we're trying to build a model which, when given these spectrograms, is able to say whether the patient is PD or healthy. Now that we have a clear understanding of our problem, we could go ahead to build the data generator. So there we go. We have this data generator which has been defined. It takes in a data folder, byte size, in one into, and the shuffling, but I will take this off. So we have just this. To better understand the in1 into, let's look at this code right here. In this, we're printing out the shape of the spectrograms. Right here, we have the spectrogram of shape 20 by 257. This other one, 21 by 257. Now, this difference is simply because we have a different number of points in this different TXT files. As we had seen previously, not all TXT files have the same number of points. So if we take this, for example, this one, let's modify here and put out 2, and then let's take 16. So we have our PD, which is 16, and we shall just shape. There we go. So we have 2055, and then when we put out, say, 17, you see we have another value, 4220. So it's normal that if we're using this PD, we would have a different number of our shape for our spectrograms. As you can see right here, now we have 15 by 257, 25 by 257. So our idea now is that when resizing or reshaping these spectrograms into a fixed shape, we're going to have this fixed value 257, which is maintained throughout and which corresponds to the frequency axis, while this one, which is variable, is going to be fixed to a certain value. And the value we've decided to work with is that of 32. And that said, in1 equals 32 and in2 equals 257. Let's modify this name to data folder. Right here we have data folder, and that's it. So we've had this, and then we'll move on to this len function. This function actually is responsible for telling us the number of times we have to go through our full data set, since we're processing data in patches. And so to get this, we simply have the len of our data set, which is gotten from this data list right here, which in fact is made of all the different files in the data folder. So we have the len of that folder, or the number of items we have in the folder, divided by the batch size we choose. So if we choose a batch size of 1, this len will simply output the total number of files we have in the folder. Now we have this get item, which permits us get each and every item. We just call in the data generation method. Here is it. We call the get spec method, which we just defined previously. So it's similar to what we've seen already, with the difference that now we resizing such that we have the spectrogram, which is outputted from the get spec, and then we convert this, or we resize it such that it gets the shape 64 by 64, since we've defined in1 and in2 to be equal to 64. Now moving into this data generation, our aim is to do something similar to what we had here. So what we get is we pass in a particular file, and then we generate the points. After generating the points, we generate the spec or the spectrograms. So we generate this, and then we now generate the spectrograms right here. So that's it. As you could see right here, we simply go through our data set based on our batch size. So we have this batch size. We go through each and every batch. We define this index right here, which comes from this index we had here. We pass the index, and say for example the index equals 0. We're going from 0 to 0 plus 1, which is 1, to the batch size. So if the batch size is 32, or the batch size is say 4, we're going from 0 to 4. We take the first 4 batch, or the first 4 elements which form the first batch, and then we move to the next. When IDX, the index becomes 1, we go from 1 times the batch size, which is 4. So it's just like we're going from 0 to the batch size. Suppose the batch size is 4, so we'll go from 0 to 4, and then the next we go from 4 to 8, and the next we go from 8 to 12, and so on and so forth. Basically this is actually 0 to 3, and then 4 to 7, and then 8 to 11, and so on and so forth. So this is how we collect batches of data and process to be passed into our model, and that's why we have this right here. Now that said, we'll repeat the same process or similar process to the gen points method, where we go through our data, we create this data list right here. Upon creation of the data list, we convert it into an array, and then this step is for normalization, which we've seen already. So basically we're normalizing across each and every column. Once we're done with this normalization, we're now ready to create our final data set, which is made of the spectrograms, as we had seen already. You can see right here we have this get spec, which we've defined already. We pass in the data list, that's to pass in, take the 0th value. We have the get spec, so we put in the spectrogram into this x1, the spectrogram for the x, spectrogram for the y in the x2, spectrogram for the z in the x3, spectrogram for the pressure in the x4, spectrogram for the grip angle in the x5. And then recall that whenever we have a healthy patient, the txt file starts with a C, and when it's not a healthy patient, it starts with an H. So what we're doing here is we're simply saying for the output we're gonna have a C. That's if the first character in our string is a C from this data list, which we've defined already. We defined this data list here, so this is our data list. We could change its name so we don't have this conflict. So we could call this file list. So we have the file list. That's it. Here's file list. That's it. We have now in here, and then okay, so we have the file list defined there, and then here we have this file list. So that's fine. So we've corrected that, and then what we're doing is, if we have a C that is a healthy patient, then our Y is a 0, so we append 0 to Y, or we append 0 to this Y list which we've defined. And the case where it's different, we append a 1. So 0 is for healthy, and then 1 is for the Parkinson's disease patient. From this, we could also modify the way we're doing this with a for loop. So you could always use a for loop, so you don't have to rewrite this way. Now that said, we have our outputs. We have the x1, we convert to a tensor, x2, x3, x4, x5. So here's our input. That's it. This is our input here, which we could define as x. So we could define our x. We could say x equals this. So let's take this from here, copy this. That's fine. And we'll define this to be x. So x is this list, and then there we go. So we have x, and then we have y, which when we output gets in here. So this is our x here, and this is our y we return, and that's fine. The next step is to define this train images and the validation images, all the train data, and the validation data. We had seen we had looked at these folders previously and would seen the contents of these folders. We also have in1, in2, we've seen already, the batch size defined, number of epochs 20. The train generator now is created, so let's run this. We created the train generator, which is this data generator right here, which inherits from this sequence class in TensorFlow.keras.utils. So that's fine. We'll run that, and then we'll run this. Let's correct that. Train data, and here we have train validation data. So that's fine. And with this, we've gone through the data preparation, data creation. We've understood the data, and now we're going straight into the modeling. The model will consist of a conv1d layer and a dense layer. The conv1d layer will be for the feature extraction, while the dense layer will be for classification. That said, considering we have these inputs, this is for x, here is y, here is z, here is p, that's the pressure, and here is g, that's the grip angle. Recall that we had seen how to leave from the txt files into this spectrograms, wherein each one of these values or each one of these features is represented by a spectrogram of shape 32 by 257. The B right here is for the batch size. And so what we're trying to do is we're trying to build a model such that we pass in these inputs, and then in the output we are able to say whether the patient has the Parkinson's disease or not. That's why we have a value of 1 right here. So we are either getting a 0 or a 1. Now that said, let us go ahead to see what the model is about. Right here we have this extractor. So for the x, we pass this into an extractor, this into an extractor, this into another extractor, and so on and so forth. And then we get this output of shape batch size by O1, batch size by O2, so on and so forth. Note that since these inputs all have the same shape, then O1 should be equals O2 equals O3 equals O4 equals O5. Let's now look at each extractor in depth. Supposing we have this input batch size by 32 by 257, we've seen this already, spectrogram. We pass this into a conv1d layer. And the way we look at this generally is that we have an input which is of shape batch size by the time dimension by the embedding dimension. In this case, the embedding dimension is a frequency. So we have batch by time dimension by frequency, which is batch by 32 by 257, which is passed into the conv1d layer. Now that we have that, we now have this output right here, batch by 32 by f1. f1 is a value which we shall see in the code. So we'll get those values automatically in the code. And then we take this again and pass into this other conv1d layer. We have this output, and then finally we flatten this to obtain this output right here. Flattening simply means we are gonna convert this 2D array that's 32 by f2, that's having a shape 32 by f2 actually, into just a 1D array of shape f3. So that's the role of the flattening layer. So we'll flatten this, and all this now constitutes the extractor, which we now have right here. So that said, we understand exactly how or what's going on in this extractor we have here. So we get past this, and then passing through this extractor, we have this output, this the same on up to the last value, or up to this last feature right here. Once we have all these values, we concatenate them to form another array of shape batch size by 06. So we've concatenated all this, and simply 06 is equals 01 plus 02 plus 03 plus 04 plus 05. So we've concatenated that, and then we pass this through the dense layer for classification. So we're done with the extraction. Now we're doing the classification part of our model. So we'll pass this through a dense layer, and then we have this output, we'll pass through another dense layer. This other dense layer here is created such that we have this output tensor of shape batch size by 1. And so this means the total number of output neurons in this dense layer is equal 1. Diving deep into the code, we define this conv layer right here, which subclasses the model class. And then in here, we define this 1D convolution, number of filters, which is going to be passed. And then the filter size equals 5, pattern same, activation ReLU. So we have that, and then we have our call function, which takes an input x, and then it's passed into the conv layer to give us an output, which we have as x right here. Now note that this is a conv layer which we had defined, and here is it called. Let's now go ahead to run this, and then we'll move on to defining the full model. So right here we have the inputs. As you could see, we have in 1, in 2 we define a shape for values in range 5, since we have 5 different inputs into our model. We define this x out, this empty list right here. We'll see shortly why we need that. We go through this 5 times. Recall that we're going to create the 5 different extractors. So here's our extractor, which we saw in the slides. We have the conv1D, the conv1D, and then the flatten. So that's why we need to do this, and it takes in each and every input. That's why we have input I. It gets into this conv layer. We define the number of filters. You can see here, number of filters 4. Next one 8, and then we flatten. After flattening, we pass this into this list x out. Then once we have the x out, as you can see right here, we concatenate this, and we consider the last axis. So we concatenate on the last axis. Once we have that, we pass this to the classification, like the classification module, which is this. So in this, we have the dense layer. It will define this, or we give it an output of 32, and then this other one, the output of 1, so that we could do the classification properly. Note that we also make sure the activation here is a sigmoid 1. So that's it. We've simply used the functional API which comes with TensorFlow, and then we define the model. See here we have this model. It takes this inputs. We have the output, which takes this output right here, and then we could have a model summary. We're told the conv layers is not defined, so let's check that out. Let's take this off. Conv layer. Let's correct this error. We have the conv layer, so that's it. And there we go. We have our model summary right here. As you could see, we have this inputs. So yeah, our inputs, and then you'll notice that we have this inputs passing through the different extractors. Since we have 5 different extractors, we have the first, that's 1 2. Since the extractor is made of the 2 conv layers, so we have 1 2 3 4, and then 5. So you have the 5 extractors. We have also 5 flattens in each extractor. And then we have the concatenate. So we concatenate those outputs to get this. As you could see, if you multiply 256 by 5, you should get this 1280. Or if you just simply add them up, recall in the slide we just added this up. If you add this up, you give it this value. And then we pass this through a dense layer, which has output. And then finally into this dense layer, which has an output shape of batch size by 1. So that's it. We have 67,000 parameters. Now note that you could always increase that. Make sure that you're working with, say, a dense layer of a higher number of output neurons, but be very careful as you may overfit your model. In our case, we have a data set of just 77 data points, which is very small, so we don't want to create a very large model, since obviously deep learning models generally do best when fed with so much data. So that's it. We're done with this section on modeling. We now move on to the next section. In training and optimization, we define a learning rate of 0.001, and then we compile our model. Right here we're using the Adam optimizer. Our loss function is the binary cross entropy loss, and then the metrics are the binary accuracy, precision, recall, number of true positives, number of true negatives, number of false positives, and number of false negatives. Now the reason why we're using the binary cross entropy right here is because we're trying to solve a binary classification problem in which we have two classes, that is the one with PD and one which is healthy. PD is a Parkinson's disease, so either a patient is having the Parkinson's disease or not. And since we have these two classes, it's a binary classification problem, and so we use a binary cross entropy loss. For the same reason, we use the binary accuracy and then this other metrics right here. We're going to see shortly why we need to evaluate our model based on these other metrics instead of just working with just this binary accuracy. So let's take this off. We compile the model, and then we have the training. Right here we have this checkpoint file path where we're gonna be saving the model as we train. So we're gonna do this using this callback, this model checkpoint callback. We define this file path. We're gonna save the weights only. We are monitoring based on the validation accuracy, and the mode is maximum. So what this simply means is, as we train, we are gonna store the model weights for which we have the maximum validation accuracy. So that's it. We now have this model of fit. We define the train gen, which we had seen already, and the validation generator. So here we have our validation data, which is equals this, shuffling through, number of epochs defined already, and then we have this callback right here. We have this checkpointing callback. Run this now, and our model starts training. So let's modify this right here because we're having this error. We've been told that, or this warning, that we cannot save, or we can only save when we have validation accuracy, because this isn't part of the metrics. The actual name, we have to take it from here. So if we look at this, we have the val binary accuracy. So we copy this right here. Let's copy this. Oh, let's just put it out here, val binary accuracy. So that's what we're supposed to put out so that the model is going to be saved. So let's interrupt that kernel and restart again. We see now that the model is being saved as there's no warning. Nonetheless, this looks very choked up. So let's go ahead and just pick out this one. Interrupt. Let's just restart the training again. So let's redefine the model, recompile, and then restart again the training. We are now done with the training. We can now take out some plots to see how this looks like. Run this. For our loss, we see how the training loss keeps dropping while the validation loss diverges for the first epochs, and then finally starts or just picks up this fixed value right here, but it's not really fixed as it's dropping. We could see from here we have this 0.919189. See, it's dropping. So that's it for the training loss and the validation loss. And it's also important to note that we expect our model to overfit since we don't have enough data to train on. So that's it. We have now the accuracy. We have accuracy. You could as well do a subplot such that you have those two plots side by side. Let's just quickly do this. Binary accuracy. And that's fine. So yeah, we have the model accuracy instead. Accuracy. I'm gonna run that. Accuracy. So here's okay, binary accuracy. Run that. Okay, here we see again that the accuracy for the training set increases up to 1. So you could see here our accuracy increases up to 1, while for the validation set, it gets its maximum value at this and then just takes this fixed value right here. And since we decided to save our model weight at this value, that's what we decided to do. Was we say, okay, we want to save our model weight when its validation accuracy is at its maximum. So what this means, we are gonna take or use our model now at the point where its validation accuracy was about 0.87, and the train accuracy, if we could do this right here, it's about 0.97. Let's check on this. 0.87 for the validation. 0.87. It's rather 0.85 actually. So here we have 0.85, and then the binary, that's the training accuracy is 0.96. So that's it. We're gonna actually work with this model at this state. So the training after this wasn't useful because this is the model state we are gonna be using, because at this model state, the validation, or we have the best performance for our validation set. Let's now go ahead to explain why we will need this other metrics. Supposing we have in the accuracy, we have the precision, and we have the recall. To better understand the precision, let's take this formula. The precision equals the number of true positives divided by the number of true positives plus the number of false positives. But then, what is a true positive? This is true positive. A true positive is a person who has the Parkinson disease. That's a person with the Parkinson's disease, and the model predicts that that person has the Parkinson's disease. In other words, we have the actual is equals 1 and the predicted is equal 1. In this case, we've seen from the data right here that when you have the Parkinson's disease is 1, and when you don't have, or when you're healthy, it's 0. But note that if we had, say, healthy to be 1 and then Parkinson's to be 0, every statement we make right here is still verified. So we have actual when actual is 1 and then the predicted is 1. This is known as a true positive. And then when the actual is 0 and the predicted is 0, this is known as a true negative. When the actual is 1 but the predicted, so actually the person has a Parkinson's disease, but the model predicts a 0, saying that the person is healthy, then this is a false negative, as this person is supposed to be positive, but the model predicts 0, which is considered to be negative. So it's a false negative. Now, if the actual is 0 and then the model predicts a 1, this is a false positive, because the model was supposed to predict negative, but instead it predicts a positive, so it's a false positive. Coming back to the definitions of the precision and the recall, where the precision is true positives or number of true positives divided by number of true positives plus false positives. This tells us that if we want to maximize the precision, then we need to minimize the number of false positives. So we need to minimize this type of predictions where it's actually 0 but we predict a 1. By minimizing this, it simply means if a model is highly precise, then it means that model is one which every time it predicts a positive, then it is actually a positive, because highly precise means low false positive rate. So whenever you're negative, it's not going to predict a positive, and that simply means every time it predicts a positive, then it's actually a positive. Now looking at the recall, we have still true positive divided by true positive. Notice how we always have true positive here and then right here. What makes a difference in this case is the false negatives. So for us to have a high recall, we need to have a low false negative rate. So saying that a model has a high recall simply means we have a very low false negative rate. And in that sense, a high recall model is one which will hardly miss out on predicting correctly a positive sample. Like in this case where we have actual 1, so this is a positive sample. A high recall model will not do this. So this is because, as we've seen already, false negative rate needs to be reduced, and if this is reduced, then whenever it sees a positive, it will tend to predict it as positive. Now, accuracy somehow comes in the middle of this too. The accuracy is some sort of jack of all trade, as it tries to minimize both the false negatives and the false positives. Notice again how here we have TP and TN and the same TP and TN down here. Let's correct this. This is TN. Okay, so we have this same right here. In order to maximize the accuracy, we need to reduce both the number of false positives and reduce both the number of false negatives. So that's what makes the difference between the accuracy and the precision recall. Now, in some problems, we'll want to have a higher precision compared to the recall. So that is, we may want to sacrifice the recall as compared to the precision, or sacrifice the recall in order to have a higher precision, or sometimes we want to sacrifice the precision in order to have a higher recall. Now let's look at our case here. In this problem we're trying to solve, we're trying to detect whether a patient is healthy or is having the Parkinson's disease. Now, as a doctor, I wouldn't like to tell a patient you don't have the Parkinson's disease when that patient actually has a Parkinson's disease. So if a patient comes in and that patient has a Parkinson's disease and we say, oh, you're healthy, and then the patient goes back, doesn't receive treatment, and then the problem aggravates. So what we want to do here is to make sure that the model should minimize the false negative rate, such that if someone comes in with the Parkinson's disease, we should not predict that the patient is healthy. Now note that generally, whenever you try to prioritize the recall as we're trying to do, this simply means we may tend to have a poor or poorer precision value. Now by poorer precision value, this means our model will be the type where you come in, you're actually healthy, but the model says you're having the Parkinson's disease. And although we're trying to train our model such that it avoids such errors, that is, we're training our model such that we always have true negatives and true positives. And in the middle of all the struggle, we have the accuracy. That's why the accuracy in our case isn't the best metric, because the accuracy is trying to reduce both the false negatives and the false positives. Whereas our number one priority is the false negatives. Now don't get me wrong, I'm not trying to say that the false positives, or I'm not trying to say that we want to have false positives. That's not the case. All what we're saying is we're just prioritizing the false negatives, or we are prioritizing the minimization of the false negatives over the minimization of the false positives. Now note that if we had defined the data such that whenever you are PD you have value 1, and when you are healthy you have value, or rather whenever you have PD you have value 0, and when you are healthy you have value 1, in that case we'll be trying to minimize the number of false positives. I will prioritize the false positives, or prioritize the minimization of the false positives. So we want to have a more precise model. But in this example, we're trying to make sure that we maximize our recall. And that said, we go straight forward into this. Let's take this off. So now we have our precision, recall, true positives. That's fine. We could restart our model again, run that, and wait our model to train. We have to interrupt this because we forgot to specify that we need this, or we need to get the value for which we have the highest recall possible for the validation. So we come to recall. Yes, validation recall. Okay, yeah, its name is validation recall 1. So let's have that. So you could, there are two possibilities. Either you take this, that's fine, or you could simply say you want to, that's like this. Either you maximize this, or you simply say you want to minimize the number of false negatives. So you could also have that, or you could pick out the false negatives. Like you could take this, and then here you specify mean because you're trying to minimize the false negatives. Minimizing the false negatives is the same as maximizing the recall. And always never forget to specify the validation here, because our training, obviously, as we see, is going to lead us to accuracy 1 and loss of practically 0. But then we're trying to get the model which performs best in the validation set. Now that set, let's go ahead and rerun again. There we go, we're done with the training. Notice how the validation recall here is 1, precision 0.75, the accuracy 0.857. So we don't again cross this accuracy value of 0.857 we had previously. We see clearly how this accuracy is in between the precision and the recall. We see our model favors this as compared to the precision. Now we're gonna explain why our recall is better than the precision, and will always be better than the precision. Now the reason why we have this is because our data is imbalanced. That's why from the onset the data we're using is not the best, because apart from the fact that it's very small, it's also imbalanced in the sense that we have just 15 points, data points for the healthy patients, and we have the other 62 data points for the sick patients. Now this means that while training our model is going to get more of these samples, and since it gets more of the samples, it would tend to favor these samples while doing the training. So the model weights will be adjusted in order to favor this samples it sees more. And that said, it would tend to predict that an input is PD as compared to saying an input is healthy. And so normally with this type of imbalanced data set, we would hardly predict a 0 when the input is a 1. So the way to solve this problem is simply to get more data and then train your model on this larger data set. Now before proceeding, we are going to come up with a confusion matrix. The confusion matrix is some sort of summary of what we're trying to put out here. Let's have that. The model, let's load the model weights when he had the best values. So anyway, at the end we had the best value, but let's just run it so that in case you were doing this, you will not have any problem. So we have the checkpoint file path. So by doing this, you're loading the best, or you're loading the model at its best. So let's take this off. Or just simply comment that. So we load the model again, and then we evaluate the model on the validation set. Now we shall print out output so you understand why we pick out this indices right here. So run that, and there we go. So this is the output we get, this out right here. Now the first is loss, the next the accuracy, the next the precision, recall, true, this should be true positive, true negatives, false positive, false negatives, or rather instead of true positives, true negatives, false positives, and then false negatives. Notice how the false negatives equals 0. So that's exactly what we expect. Now the confusion matrix is simply this matrix where we say, okay, the true negatives, how many true negatives do we have? 6. False negatives, how many do we have? 0. False positives, how many do we have? 2. True positives, how many do we have? 6. So this confusion matrix simply displays what we're trying to explain right here in this simple matrix. You could always use some libraries to plot this out in a more beautiful way, but it's always going to have the same information, so we just print it out like this. So that's it. We have our confusion matrix. We can now go ahead to do some testing. In order to do the testing, we're going to modify slightly the getSpec method we had defined previously to have this resize. So we run that, and then there we go. We have this detect method right here. It takes in the file path for a given image. It's similar process we've seen already. So we've seen this already. We have normalization. We just add this up into this list right here. We have the getSpec, and then once we get X, because what we're doing here is we're creating a list which is going to take in the different spectrograms right here. So once we get that, we also add this expand dims, we add this batch dimension. Now note that before we're having outputs like this with a shape 257, but before passing this into a TensorFlow model, we need to include a batch dimension. So it needs to be like this, 257. So that's why we just add this dimension. So it's going to be 1. So that's it. We expand dims, we put it in the 0 axis such that it's going to fall in place right here. Now this is initially 0, 1. Now putting in 0 means we're just adding this dimension and then shifting this others. So that's it. Now once we have that, we have this input which is ready to be fed into a model. Note that it's also a list because our model takes in a list of 5 different elements or 5 different spectrograms, and then we pass this. We have the predict right here. So we predict, and then we get the output of this prediction, and then if the output is greater than 0.5, your PD, else you're healthy. So let's run this with this txt file from the validation set. And there we go, we have healthy. So the person is healthy. See here we have this healthy without this person. So let's include this message right here. We have this message, we have this person is healthy. Take this off. This person is healthy. Even here we could just do this. So that's it. So let's run again. We have this person is healthy. We pick out another sample from the validation set, but this time around one of a patient was actually sick. So run that. We have this person is having the Parkinson's disease. Now you should note that deep learning models generally feed on large data sets, and if you're working with deep learning models, it's important to make sure you get as much data set as possible. And in this tutorial, what we've done is we've shown you all the steps you would take if you were to put this kind of project or work on this kind of project in a real life context. But note that all what we've done will be very useless without you having a reasonable data set. And coming to the corrective measures, data is key. First thing, to correct our model or to better our model performance is to get more data. The next is class weighting. The class weighting comes in to solve the problem of data imbalance. The concept of class weighting is quite simple. What happens is whenever you have class imbalance, like in this case where we have healthy 15 and then we have PD 62, what we want to do is we want to penalize the model more whenever it performs poorly on the healthy data points. And as we had seen, or as we said previously, this is normal since the model has seen more of the PDs as compared to the healthies. So we want to penalize the model more whenever it sees a healthy, and then penalize it less for the PDs. Now, penalizing is simply saying that if previously the loss was a combination of the loss from the healthies, that's after computing the healthy, plus the loss for the PDs. So yeah, we had, supposing we had previously a factor of 1 by this and then 1 by that. Let's just normalize this to 0.5. 0.5 normalizing, just dividing by the total number of classes. So yeah, we have 0.5 times this and 0.5 by that. Now 0.5 is gotten by having 1 divided by the total number of classes, which is 1 divided by 2, which is 0.5. So that's it. Now we have this is what we have by default. So we want to modify this such that for the loss, when we perform poorly in the healthy, we have a higher loss value compared to this, such that the model would tend to be more aware of the fact that it needs to make some effort to predict correctly this loss healthy, or rather to minimize this loss healthy, so that we can minimize the overall loss. And this is simply because of this factor right here. Now in this our particular example, we may not even want to do this, because what we want to do is we're focusing on this PDs, but nonetheless it's important to understand this concept. Now, a general formula we could take is that the weight, or supposing we have two classes, class 1 and class 2. In this case, our class 1 is the healthy and then class 2 is the PDs. So in this case, we have 1 divided by the number of healthy, in this case is 15, times the total number of samples, 77, divided by the number of classes, 2. Now in this, recall that we had that normalization, so this 2 is just for normalization purposes. So we have 1 divided by 15 times 77 divided by 2 gives us 2.56. So the weight here is more than that of this one right here, which is 1 divided by 62 times 77 divided by 2, which is 0.62. And so here we have 2.56 and then 0.62. To implement this in TensorFlow is quite easy. All you need to do is come right here, or at the level of the training, you specify the class weight. So yeah, you just specify class weight. You could call it class weights, and then we have this dictionary. So we have class weights equals 0, takes in the value 2.56. It's 2.56 here, and then 1 takes in the value 0.62. So that's fine. So now let's run this. This is now what we get. We have now a higher false negative rate, which is not what we want, and this was predictable, since with the class weights we're trying to solve that problem of data imbalance, as we're trying to penalize the model whenever it sees a healthy patient and predicts that that patient is having the Parkinson's disease. But in our case, our focus is on making sure instead that everyone who comes with a Parkinson's disease is predicted by the model to actually have that Parkinson's disease. Anyway, in order for us to actually apply this effectively, we simply need to get a larger data set, and if possible, a balanced data set, so we don't even need to use this. So we could take this off and spend time getting more data. For this week's giveaway, what you'll do is show how you could use this same data but differently. That is, show how you're gonna use just the X, the Y, and the pressure values in training your model. So you're not going to take into consideration the grip angle nor the Z angle. So just show how you're going to use X, Y, and pressure by simply modifying this code. Now if you're able to do that, you could save that notebook, visit neurallearn.ai, come to this course right here, Deep Learning with TensorFlow 2. And depending on whether you want to take this course as a person or as a single learner or as a group of 3, you could apply for a scholarship, and then you attach that modified notebook to your application. Wish you the best and see you soon.